To transform the news. Is YouTube more than a collection of cat videos? Is it a force for social change? Do channels like Juice Rap News, The Fucking News, Mad Bitcoins, and the World Crypto Network provide more than just entertainment? Can they actually provide the truth? If the medium is the message, and it always has been, is it capable of being truthful? And can we use this truth to bring about social change? I'm laying it all out on the line here with this question. Can YouTube change the world? Will Pangman?
I think if they change the way incentives work for advertisements, for revenue, for the content producers, and do something, maybe integrating Bitcoin to perhaps upvote good quality comments and get rid of trolling, then yeah.
Christoph, Atlas.
Yeah, it already has. YouTube is just a way of connecting people in a more peer-to-peer fashion, exchanging ideas and information and all that stuff. It's the natural progression from the printing press to all the things in between. And of course, there are things that we can do to improve YouTube around including Bitcoin and change tip and all that other kind of good stuff. But yeah, it's been doing that for a long time. I've been getting the majority of my information through mediums like YouTube for years at this point.
Blake Anderson.
Well, yeah, I've been railing against unilateral communication for a long time. I think it's important that people can comment and respond to articles. Every time I see a modern digital publication that is an article with no area for comments at the bottom, I was like, what? Who is running this disaster? There's no place for comments. So I think that YouTube, if we can get a situation where people can talk back and forth and make shows and then come on each other's shows, and that we can have a decentralized system of communication and entertainment instead of all this unilateral programming that everybody's depressed and on antidepressants and gets all these messages about war and death and genocide and Ebola and all this shit. That's a nightmare. That's nightmare shit. We need to start to get away from that and realize that negative programming affects you negatively, and positive programming and working together in collaboration really makes people feel better, because you can feel the traction of shit actually getting better instead of just being entertained to death into your grave. So I mean, I think it's good. I think that everybody should join the World Crypto Network and donate and work together and become part of the shows, and that we should usher in a good version of the future.
Bryce Wiener.
I think there should be more boobs on YouTube. I think YouTube should allow porn, and I think that until they stop editing content, it's all just so much bullshit.
Chris Ellis.
Yeah, I'm actually really optimistic about BitTorrent. I'm looking forward to this becoming a little bit more mainstream. So I'm really into torrents again. I don't know why. I just suddenly got into it because I think somebody sort of said to me that, they've got Merkle trees in there. I was like, oh, cool, really? And so I started looking into it. I started putting everything up there because I just like the fact that it's distributed. And so now this app, apparently this open source project on GitHub by Feroz, is claiming to stream video through a web browser with no plugin required, just straight up through the web browser. It will stream you a video torrent. And I want us to do this on the World Crypto Network as soon as it becomes feasible. I'd like us to really do this because I don't think we should be dependent on YouTube's great as far as it goes, but it has been known to shut people down. People can troll you. They can also petition for you to be taken down, and YouTube just take you down automatically because they got like 10 different IP addresses to say that you had inappropriate content. So I really like like this kind of thing, and I'm also a big fan of Juice Rap Media.
And it's not even just torrents anymore; it's magnets that get you the torrent. Magnets. How the fuck do they work?
We've been publishing the magnets. In fact, isn't the next story about this lady that blew the whistle on the Fed, and I've now uploaded that to torrent, so it's now immortal.
Very cool. Exit question: yes or no? And this one's for the viewers at home too. Will you help me change the world with YouTube? Will Pangman?
Yes.
Christoph, Atlas.
I'm in.
All right. Blake Anderson.
What was the question again?
To say yes.
No.
No. Bryce Wiener.
Take your shirt off.
They're saying that now. Chris Ellis.
I think I'm going to quote Camus and say you can't change the world, but you can change the way people think.
And I'll quote Groucho Marx. I wouldn't want to be a part of any club that would have someone like me as a member. Moving on. Issue 5, bonus issue. Federal Reserve leaks tapes. Federal employees were told not to ask questions, not to regulate banks. A culture of failure. New tapes.
I turned my camera on, I cut my fingers on the way, and you wasn't playing.
So hey everyone, I'm Faraz, and I want to tell you today about WebTorrent, which is my open source project to build a BitTorrent client that works in the browser. And this is kind of madness because BitTorrent is not something that has ever worked in the browser, and so the project is definitely in the mad science realm, and it uses this awesome peer-to-peer protocol called WebRTC that has recently landed in the browser to enable this. But before we get too much more into WebTorrent, I wanted to talk a little bit about how BitTorrent itself works, because I think it's something that we all use every day. Well, a lot of us do, but it's something that for a long time I didn't really understand on a very deep level. I kind of knew, high level that you have these people out there that have the files that you want, and you somehow connect to them, and they send you little bits of it, and then you kind of like put it all together on your machine, and then you have the file that you want. But it's actually kind of cool to kind of look into how the protocol works, and so I thought we would talk about that first. So traditionally, the way that most of the services that we use every day work is the client-server model. So you have like an HTTP server, and you have a client that connects to it. It sends it a request asking for a specific resource. So in this case, file.txt. And if the server has it, it'll send back a response containing the file. And the way that we refer to all these files is using something called a URL, or a uniform resource locator. And the URL tells you where to go to get the file. So it's all about the location of the file. So in this case, the file lives at example.com. And it's our job to go and find that server and then to ask it for the file that we want. And so as more clients show up, they continue to go to the same location and ask the same server for the file that they want. Eventually, you get to a situation where the server needs to either upgrade to handle the number of requests that it's getting, or it's not going to be able to handle them all. Another issue that comes up with this model is if the server disappears, then we can no longer get the file because we're referring to it by its location. So if the location disappears, then the file is gone, and this is the jetted broken link that we all see on the web every day. Oftentimes, too, URLs will change. So the file is exactly the same, but somebody decided to name it something different or put it on a different server. And this is also undesirable. So in the BitTorrent model, we don't have a server at all. We just have clients. Everything is a client. So at some point, a file, somebody needs to decide, I want to bring a file into the network. So there's still an initial publisher, because there has to be. There has to be a person who says, hey, I want to share this file with people. But instead of putting it onto a server and then sharing a URL, what they do is they create a torrent file. And they become what's called the initial seeder. So a seeder is just somebody who is making a file available and sharing it. And they're the initial seeder because they're the first one doing that. So when clients come later on and want this file, they connect to the client and they make a request and get back a response. And this is very similar to HTTP, except it uses a different, different protocol. So we have a method, and then we have a piece index, a byte offset, and a length. And these are kind of similar to an HTTP range request, if you're familiar with that. How many of you have actually used like an HTTP range request before and know what it is? It's basically a way to say, hey, I want this file, but I only want this byte range, so send me just this part of the file. And clients often have good reasons for doing this. Like if you're watching a video, maybe you want to download starting from halfway through the video or something like that. And then there's also, similarly, there's a response that comes back, and it just confirms the piece of the file, the byte offset, and then the actual data comes last of all. And so in this model, as the number of clients increase, you'll notice that the number of connections increases much faster than the number of clients. So typically, a client will connect to more than one client. So in this particular example, it's not a fully connected graph, so every client isn't connected to every other client, but every client is connected to more than one client. And one of the things that comes out of this is that we get really fast downloads, because the protocol is, first of all, it's a really efficient design. So it doesn't send very many bytes on the wire. And it can do things like use UDP and other non-TCP protocols to make to utilize the multiple connections very well. And the best part of all is that every downloader is also an uploader. So even though I don't have the complete file, I'm sharing the bits that I do have with the rest of the network. Another benefit is it's decentralized, so there's no central point of failure. There's no place to go, and there's no server you can go and shut down to censor the network, because you literally have millions of nodes all across the world that might pop up for an hour in a Starbucks and go down, and there are just too many places, and so it's a really robust design, and it kind of reminds me of the early days of the internet. It was designed to tolerate network failures and to be kind of really resistant against attacks on certain infrastructure, routes around it, and so this is kind of like that. So let's talk about a little bit more about how that works. So this peer here is the initial seeder. They have the full file. So what they do is they split the file up into pieces. In this case, this file that they're sharing has 5 pieces. We just label each piece. And there might be other peers in the network that are downloading the same file. They might not have the full file yet. They might have only parts of it. And then we show up, and we don't have anything. And so what we need to do is we connect to these peers. I'll talk a little bit about how we do that. But once we're connected to them, we need to figure out what pieces they have. And so during the handshake process, every peer actually tells us exactly what pieces they have. And throughout the duration of the life cycle of the protocol, the peers actually keep us up to date. So every time they get a new piece completed, they'll let us know. So we have a very accurate model of what pieces the people that we're connected to have. And what we'll do is we'll just send a request to each peer and ask them for different pieces. So for peer 1, we can ask them for piece 0. For peer 2, we can ask them for piece 1, and we'll get piece 3 from peer 3. So this download will start to happen, and eventually we'll have those pieces, and then our job is to make additional requests to get the remaining pieces. And of course, during this time, the other peers are going to be completing their downloads as well, and we'll eventually get to a situation where everything is, we have all the pieces. But now we need to reassemble them, right? Because we got them and they could come in a random order. And so we just put them in the correct order, which is pretty straightforward. And now we have the full file. So a couple of other things we can do to make the protocol more robust, and these are things that all existing BitTorrent clients do, is we can follow a tit-for-tat model. So what this means is we help the peers that help us. So if there's a peer that is being kind of stingy, we ask it for a piece and it just decides to never reply to us, we'll take note of that, and we'll be less likely in the future to answer their requests. And this is kind of like a model where every client kind of has its own self-interest, at heart, and it helps those who help it. And one of the cool things that comes out of this actually is that you can kind of do a little game theory, and every client kind of tries to game the system to get the fastest download speed that it can get. I mean, this actually helps the network as a whole. So what I mean by this is every client's actually trying to download the rarest possible pieces that it can find. So let's say there's a piece that just for whatever reason is, fewer people have it on average. If your client goes and gets that rare piece, then suddenly it's become a lot more desirable to the rest of the peers in the network. Because that piece is just not as available, so you're more likely to get connected to, and you're more likely to get that piece requested. And so that means that those peers that are connecting to you have an incentive to be nice to you and to trade with you, and that's really cool. So also, if you look at the whole network level, this is actually really good for preserving the health of torrents in the long term. So as a torrent ages, there may be fewer seeders. Actually, at the beginning, too, when a torrent first gets put up, there's also very few seeders. And in both of these scenarios, there's a chance that if those seeders go offline and disconnect for whatever reason, that the torrent will become incompletable. So this means that even if all of the remaining peers in the network pool all their pieces and share amongst themselves, there might still be some piece that just disappeared and no one has it. And that's really bad. That's a really bad situation to be in. And so by downloading the rarest pieces, we decrease the likelihood that this bad situation is ever going to happen. And lastly, we can preempt slow peers. So what that means is if a peer is being really slow for whatever reason and taking forever to give us a piece that we requested, we might say, well, why are we waiting for this person? Let's request that same piece from an additional peer. And so we might be actually asking for the same data from multiple people at the same time, if we deem that this is a really important piece that we need to get. And this will come into play when we actually do streaming, where we'll download a torrent sequentially in order to play it back in a video player, which is really cool. So how do you refer to a torrent? So there's no URLs for torrents, right? There's no you don't refer to them by their location, because the location is millions, potentially hundreds or thousands of peers around the world. So instead, you refer to a torrent by what it is. So you refer to it by its content, not by its location. So what I mean by that is we have these little things called torrent files. You've probably seen them before. They're a little file. And if you've ever bothered to open them up in a text editor, you'll notice that there's a lot of data inside those files. And so the important stuff that's in there are the name and a list of all of the pieces in the file. So the initial person who created this file, this torrent, what they did is they split up the file into all of these little pieces, and then they hashed each piece using a cryptographic hash function. In the case of BitTorrent, it's SHA-1. And they produce these little hashes, and they put them into the torrent file. And this means that once I have my hands on this torrent file, I can get data from anyone on the network, and I can verify that the pieces that they've sent me are what I was supposed to get, because I already know the hash of the content. And then the last bit is there's this announce field, which tells you where to go to find peers. In this case, it's a server, tracker.example.com, which is a place where we can go and say, hey, tell me the peers that I should talk to get this content. Now that's a point of centralization that's not ideal, and we'll talk about how we can get rid of that in a sec. But so one thing you might have realized is that this torrent file is not really succinct, right? A URL is kind of nice. You can copy and paste it around and stuff. But with the torrent file, it's kind of this big, messy blob of data. And so what people have done is there's a really succinct way to refer to a torrent. And what you do is you just hash the whole block of data up there, and you get what's called an info hash, which is just one hash that can refer to the whole torrent. This is actually how magnet links work, if you've ever seen those. So real quick, let's just review cryptographic hashes, because this is how we verify that we're getting the correct data. So I'm probably boring some of you, but it's basically a one-way function where you have the same input always produces the same output. And given an output, it's really hard to find what input produced it. So this means that when we're trying to download a file, if we ask a peer for a piece, and we're expecting to get a happy face, we know what the hash of that is. We know we know when we hash the content that we're looking for it to be this particular hash. And if some malicious peer on the network decides to send us the wrong data, like a sad face, and they've changed it, manipulated it in some way, when we hash it, it's going to turn into something different, and we'll know, okay, I can throw this away, and I'll mark this peer as untrustworthy and never talk to them again. And so the hash that we produced for the torrent file, that info hash thing, is used by a tracker server. And what the tracker server does is it keeps a mapping where the key is the info hash, and the value is an array of all of the peers that are interested in that torrent. So when I say interested, I mean uploaders and downloaders. So these are people who either have the complete file or are trying to get the file. And a client just tells the tracker, hey, I'm interested in this file. Please add me to your array of peers. And then next time someone comes along trying to download that file, the tracker will send them that array, and then they'll know who they should talk to. So like I mentioned, this is kind of not ideal. It's a point of centralization. So let's just compare it to HTTP and see kind of why, what is the difference between BitTorrent and HTTP. So with HTTP, you find URLs through central means. You go to a search engine, you go to Google, or your friends email you a link. There's no kind of way to kind of discover links. You just have to trust someone to give you the link. Same thing with torrents. You go to a search engine, your friend emails you a torrent file, something like that. And then when it comes to finding peers, well, in the case of HTTP, it's not really a peer. You're trying to just find the IP address of the server. We use the domain name system. And that is distributed but not decentralized. So domain name system, it's many servers working together, but it's still not, it's not robust against like censorship and things like that. And in the case of torrent files, again, we're going to a tracker server and asking it to tell us which peers we should talk to. Not ideal. However, we do get decentralized file transfer. So we're getting the data from many, many peers, and that's pretty awesome. But we can do better. This is where magnet links come in. So with magnet links, we use something called the distributed hash table to find peers. So we can actually eliminate the tracker server. So with magnet links, we can actually go from just having the info hash, so this little 160-bit string, we can go from that to having the full file without really ever talking to a server. And that's really, really cool. So what is a DHT? So I think DHTs are so cool, by the way. DHTs are like one of the coolest ideas in computer science. Like when I first discovered what a DHT was, I was telling all my friends about it constantly, and everyone was like, dude, you're a huge nerd, stop telling me about this. I even actually, when I went in for a job interview, I got off track and started explaining what DHTs were to the interviewer, and they were just like, dude, what are you doing? So they're really cool. So they're basically just a distributed key value lookup. So in JavaScript you have objects, and you can set properties on them, right? And then you can use it as a key value lookup. Well, a DHT is just that, except the storage is across millions of nodes all over the world. And when you want to do a lookup, you actually have to go out and find those nodes, and then tell them the key that you want to look up, and then they'll give you back the value. What's cool about it is you can basically turn all of the peers in the BitTorrent network into mini tracker servers. So everyone is tracking a certain subset of torrents, and they're keeping that mapping of torrent hash to array of peers. It's also really, really efficient because it uses this system called Kademlia, which is written about in a research paper, and it has provable performance characteristics that are really good. So it's like O of log n, where n is the number of peers in the number of nodes in the network. So let's talk about how it works, okay? It's really cool. I created a little visualization. Hopefully it does a good job of explaining it, but we'll see. Okay, so the way I think about it is we have a big number line, okay? And the number line goes from 0 to 2 to the 160th power. And the reason why it's 2 to the 160 is because that's the space of possible numbers that you get when you SHA-1 something. So a SHA-1 hash is a 160-bit, has 160 bits of randomness. So when you hash something, it will produce a hash that's somewhere on this number line, right? So when we first boot up our torrent client, it chooses an ID for itself randomly. So in this case, let's say we boot up and our ID is somewhere over here near 2 to the 30th. So we're somewhere on the number line. Cool. Now throughout the course of the protocol, we're going to be introduced to various peers. And as we discover these peers and talk to them, we add them to our table. So let's say we find a peer here, find a peer there. We keep adding them to this table. And basically what we're doing is saying, this is their ID. It falls here on the number line. And this is their IP address and their port. This is how I can talk to them. Now, obviously, we don't want to just add everyone that we talk to, because there are millions of nodes. There's actually like 10 or 20 million nodes in the BitTorrent network at any given time. And so we can't store all of these, and that's just a bad idea. So we need some way to decide what to store. So what we do is we create this, we have this notion of a bucket. And every bucket has a maximum size. So when we start out, we just have one bucket. It's the whole number line. And let's just, for sake of this demo, let's say that our bucket size is 4, but in practice it's usually something like 8 or 16. And we don't want our bucket size to ever surpass k, or 4. So when we get a new peer, and if adding them would make the bucket have k+1 nodes in it, then what we're going to do is check and see, is our ID in the bucket? So are we in this bucket that we're about to add this peer to? And if the answer is yes, then we'll split the bucket in half, exactly in the middle, and then now we'll have 2 buckets. And then we'll add the peer that we just discovered to whichever bucket they go into. But if we're not in the bucket, then what we're going to do is ping all the peers that are in that bucket, send them a ping message, and see if they respond. If one of them doesn't respond, that means that they've gone offline. Then we're going to delete them from our table, and we're going to add the new peer. So this is cool because we end up keeping nodes in our table that are long running. So we'll never replace a good node that's online with a new node that we've just discovered. And then if all the nodes are online and they're all good, they're all healthy, then we're just going to throw away this new peer. We're going to say, too bad, I'm not going to store it in the table. Just going to throw it away. So let's take a look at how that would work. So we have our hash table here, and let's say we learn about a new peer. So this is the 5th peer. This would, we don't count ourselves. So there's 4 peers currently in the table, and now we discovered a 5th. That's k+1. That's too many. So now we need to decide, are we going to keep it? So we say, are we in this same bucket? And yes, we are, because there's only one bucket. And so we say, yes, we're going to keep the peer. We split the bucket into 2, and we add the peer. Now, time goes on. We continue to discover new peers. Cool. Now, again, we get into a situation where we discovered another peer. There we go, yeah. And now we need to decide, are we going to keep them again? And we ask ourselves the question, are we in the bucket? And this time, no, we are not in the bucket. This is the bucket that we're not in, because we're the star. So we're not going to keep this peer. We just throw it away. And so this continues. This keeps continuing. And eventually, you get into a situation where this is kind of how the table will look. I ran out of space. This in practice would be very, very much bigger. And you end up noticing that the buckets get really small around your ID's location. And since all the buckets contain the same number of nodes, you end up having like a lot of information about the peers that are near your own ID. The table is really dense there. OK, cool. So now let's talk about what operations you can do with the DHT. So the whole point of this is that this is a key value store, right? So when a peer connects to us, they can send us a put message that says, hey, please put this value at this key. And what we do is we look at the key and we say, is this key near our own ID? And the reason why we do this is that, so remember I said all the peers are acting as miniature tracker servers. Now, everyone is responsible for a certain range of torrents. So if my ID is near 2 to the 30th, I'm only going to be responsible for tracking torrents that have IDs that are near my own ID. So I'm not responsible for storing keys and values for like any torrent, only the ones that are near my own ID. So when someone tries to put something, I will look at it and say, am I actually responsible for this? And if I am, I'll store the key value in my own table. And if I'm not, I'll just throw it away. And so this is what a put message in practice would look like. So this is some peer saying, hey, I'm interested in this torrent, this info hash here, and this is my contact information, my IP and my port. And I'll store that. And so the DHT storage looks exactly the same as tracker storage, except you'll notice that, like in this example here, I'm tracking 2 torrents, and they both start with the same prefix because they're near my own ID. Now to actually do a lookup in this table, to actually do a lookup in this table, we have to do a bit we have to have an algorithm. So we pick the k closest nodes to the key that we're looking for. And so we have our table, right? And we know about some peers. In some areas we have a lot of knowledge, it's really dense. Some areas it's not very dense, whatever. We just pick the k closest that we know about, and we send those people a lookup message. If they return, if they're not actually responsible for tracking the key that we asked them about, then they'll say, sorry, I can't actually tell you any peers for this torrent, but what I can do for you is I can tell you about nodes that I know that are closer to the key that you're looking for than me. And so they'll tell me, hey, you should try talking to these guys, they're actually closer. And so then when I get those back, I'll actually send lookup messages to those people, and I'll continue recursing. Eventually, I will get to someone who can actually give me peers. They can say, hey, these are the IP addresses and ports for the guys you're trying to look for, and that means that I actually found the peers that are the trackers for this torrent. And then at that point, I'm done, and I can connect to those peers. Awesome. Cool. So this all works, and it's efficient because the nodes are dense around, have a dense number of peers around their own ID. So as I kind of recurse over this algorithm, I'm kind of honing in very quickly on exactly the people I'm trying to talk to, and it has really good performance. It's, like I said, O of log n, and over time, your table will fill up with stable, long-running nodes. And obviously, there's one thing we didn't talk about, which is how do you get your first peer? Like, if all you have is the hash of a torrent, you need to how do you find the first one to talk to? And for that, we need to use a bootstrap server, which is again a point of centralization. You're always going to have something somewhere, but we've minimized it so much to the point where as long as you know someone's IP and port, that's it. You're bootstrapped into the network, and you can discover everything you need from there on out. And so in practice, so this is what a magnet link looks like. And it says magnet, it says URN, which means uniform resource name, and then BTIH is BitTorrent info hash, and then it has the hash. And that's it. But you can also add a little bit more data in there if you want to be friendlier to the person's BitTorrent client. So one param that you often see is DN, which is display name, which means show this name in the interface. Now, the reason why you need to do this is because, so remember the torrent file we talked about before, how it had a name field? Well, with magnet links, you don't have a name field, right? You just have the hash of it. And there's going to be maybe a minute where you're going out into the network and you're asking people, hey, can you send me the torrent file for this? I only know the info hash, but I don't have the torrent file. I don't know the list of pieces. I don't know the name. I don't know anything about it. I just know it's hash. So please give me that metadata. And during that time, your client won't even be able to tell you what the name of the thing you're downloading is. So when you add the DN parameter, it'll show that up in the client, which is pretty cool. And you can even add tracker servers in here if you want to get peers even faster. So they're not kind of an either or thing. So cool, so this is where we're at. We've managed to decentralize the finding peers part, but the search is still not decentralized. This is an unsolved problem as far as I know. I know there are some people who are attempting to solve this, but I've never seen it really done well, and it's certainly not a mainstream thing in the BitTorrent community. Cool, so thank you for indulging me in the DHT stuff. Now I should get back to talking about WebTorrent, which is why I was invited to speak here. So what is WebTorrent? So, I've talked a little bit about kind of how the protocol has evolved, where we've eliminated these points of centralization in finding peers. But I think the next evolution of BitTorrent needs to be making it easier for normal people to use. So I want it to be as easy as going to YouTube and watching a video. Yeah, I think we should watch that again. It's definitely worth another rewatch. Anyway, so yeah, I want BitTorrent to be something that's as easy as going to a website and pushing play on a video and just having it play right away. And we're a long way off from that. So currently, the the experience is you need to go somewhere, download a torrent client, install it on your machine. Then you need to go find a search site, search for what you want, and then you need to get a weird file, download it, and then open it up in this program. Then it asks you some questions. Where do you want to save it? And then you wait an hour, and then you finally can go find it on your file system and open it up in a media player or whatever. It's not very friendly. So with WebRTC, a new a protocol for the web, we can actually do this. So what is WebRTC? Let's talk about how WebRTC enables this. So Justin Uberti, this Google engineer, talked to Google I/O, and he described WebRTC as a project to bring real-time communication to the open web platform. So what this means is you can do peer-to-peer video, audio, and data in a browser without any installation. So this is part of the web platform. It's currently built into Chrome, Firefox, and Opera, including all of their mobile versions on Android. So Chrome, Firefox, Opera, including all of the mobile versions on Android. So this means that there's billions of devices today that already support WebRTC, which is really cool. But what about IE? So IE has this really cool status page nowadays. You can go to status.modern.ie and see what Microsoft is working on and what they think of all the various specs. And recently they announced that they plan to implement WebRTC, which is awesome. But the version of the API that they're implementing is kind of like WebRTC 1.1, and they're just going to skip over 1.0 completely. And so it remains to be seen kind of how easy the two APIs are going to be to shim out, but it's going to be possible to make this work in IE as well, which is awesome. Apple hasn't said anything yet about what they think of WebRTC. So common things that you'll see WebRTC being used for, things like video chat demos, where people will basically implement Skype in the browser. And that's pretty cool. But what I'm more interested in is being able to just send arbitrary data to between browsers and implementing the BitTorrent protocol using that. So I don't want to just ask the user to turn on their webcam and use their mic and then do a voice chat. I want to be able to send whatever data I want to send between browsers and do it without going through a central server, because with that I can build BitTorrent. So the way this is going to work is, so we have all these BitTorrent clients that are out there today in the world that are installed on people's computers, and they speak the BitTorrent protocol to each other. And this protocol, has a lot of variations, but in general, the way to think of it is it uses TCP and it uses UDP to talk to other clients. And this doesn't work in the browser, obviously, because of security reasons. So WebRTC kind of mandates a different model where I'll get into it in a bit, but it's a more complicated connection setup process that ensures that that the browser you're talking to really wants to receive a connection from you. And because it's so different, there's really no way to actually get a browser BitTorrent client to talk directly to a normal desktop BitTorrent client, unless that desktop client does a little bit of extra work to talk to the web peers. And so the plan to roll this out is to build hybrid clients. So hybrid clients are going to be desktop BitTorrent clients that people will install that can talk the BitTorrent protocol. But also, we have these other clients, which are web browsers that only speak WebTorrent. And so they're running in a browser. They're just literally a JavaScript script tag on a page somewhere, and they're talking to each other, sharing files amongst themselves. And they can also talk to the hybrid clients, because the hybrid clients can talk to both. So when a hybrid client is downloading a file and then becomes a seeder, they're seeding it to both networks, both normal BitTorrent network and the web network. And I'm hoping over time that there'll be a lot of hybrid clients and everyone will want to implement this. But to start with, I wrote the first hybrid client. So just to emphasize, this is not possible. You can't make WebRTC work with TCP and UDP without building some kind of centralized intermediary, and we don't want to do that. So these hybrid nodes are really important because they actually bring content into the web network. Without them, these web peers are kind of ephemeral. They kind of show up and disappear very quickly because they're in a browser tab. When the user closes the tab, suddenly that seeder goes away. So the hybrid clients are really important. So I want to show you guys what it would look like to actually use the WebTorrent API to actually build an application, just so you can kind of get an idea for how easy it is to actually work with. So I've built a Node module called WebTorrent. You can use it in Node and in the browser, and it's the same module in both places, which is super cool. So when you require it in Node, you get a BitTorrent client that you can just use to download whatever you want. And if you require it in the browser, you use something like Browserify to build it, then you're going to get a client that is almost exactly the same code, except for it uses WebRTC to talk to other peers, and it can only talk to other web nodes. And let's see how that works. So, cool. So I have some code here. Here we go. Cool. So what we're going to build is a file sharing app where I can drop a file on my browser, and then the browser will create a torrent and will give me the info hash of it. And then I can just send that to my friend, and they can go to the same site and type it in, and then they're going to connect to the WebTorrent network, and they're going to find that user's browser, and then they're going to pull the file directly from them. And then they're going to become a seeder. And then a third browser could come along, and then they would be able to download from both of those existing browsers. So this is like the full BitTorrent protocol, but just over WebRTC. So let's do this. So to start with, we're going to require a module called drag drop. And this just lets us support the drag and drop API with a really nice API. So I'm going to require drag drop / buffer. And what that means is once the user drops a file in the browser, I want to actually get the file back as a node-style buffer rather than the browser's really weird blob API, which I don't like. So I'm just going to say when the user drops something on the body, please give me call this function with the array of files that they dropped. Next, we're going to require WebTorrent. And we're just going to create a new client. And when the user does the drop, we're going to call client.seed with the files that the user dropped. So we will become the first seeder for this content. And this is going to go ahead and create a torrent file. And then it's going to call onTorrent once it's done that. And it's going to pass us that object. And we're just going to just log that to the page and say, yeah, we have a torrent. This is its info hash. Cool. Next, let's create a form on the page so that the user can paste in an info hash, and then they can download it. So we're going to create an event listener here, and when the user submits the form, we will call client.download and pass in the info hash. And what you'll see me doing here is, in addition to just passing in the hash of the torrent, I'm also saying, please use this tracker server here that I set up. And the reason why we're doing this is because currently we actually haven't implemented a DHT that works over WebRTC. So we have trackers. So we're saying, please use this tracker here. And you'll notice it's using the WebSocket protocol because that's a more kind of web-friendly way to do a tracker server. And also with WebRTC, we need the ability to push data to peers. And I'll talk about that in a sec. Anyway, so then again, onTorrent will be called once this user has found the metadata for the torrent that they want to download. So here's the seeding code, and here's the downloading code. It's really simple, just client.seed and client.download. Next, we're just going to iterate over the files that are in the torrent and we're going to get each of the files and create a stream. So a stream in Node, is just a way to get the data out of a file sequentially. And we do this to get the actual content because we want to show it on the page. So the way we're going to show it is we call create read stream, and then we pipe that into the concat stream module. So concat stream is just required up here. And that will kind of collect all of the data that's coming out of the file and give it to us as a buffer. And once we have that, we're going to just insert it into the page by creating a link and using the create object URL browser API to take a buffer of data and to turn it into something that we can link to from the page. And then we just insert it into the page. That's it. And you can see the HTML for the page is right here. It's pretty straightforward. So let's see what that looks like. So here's a site that's live right now that you can actually go to, and you can test out WebTorrent. So you just go to instant.io, and we just drag a file onto the page to become the first seeder. So I'm going to go to my desktop here, and I'm going to grab this cute cat, drop it onto the page. So now it's saying, hey, you're the first seeder, and I can click this to confirm that the file is being correctly parsed by the page. Awesome. Now I'm going to take this info hash. I'm going to open another tab, and I'm going to paste it in here. I'm also going to just open up this inspector so you can see what's going on. And when I click download, it's going to find the peer from the other server and then download it. You can see it got the file here. This was done peer-to-peer directly, from one browser tab to another. Thanks. So one other thing that I added to this that's super cool is you can actually stream video data. So you don't have to wait for the file to be fully completed before you can start watching. And you can do this with the video tag. They're using this thing called the media source API. So the way it works is you can get video data, and you can just shove it into the video tag as you get it and say, play this, play this, play this. And the video could be really long, and it'll start to play back immediately. And to do this, the client has to be smart about the pieces that it asks for from the network. It has to request them in order instead of requesting rarest first, like I talked about before. But you can see this in action too. It's pretty cool. So I'm going to do this again, but this time I'm going to include a video file here. OK, cool. All right, yeah, so I don't have sound, but that's OK, because it's playing really loud dubstep right now. You don't want to hear it. All right, now I'm going to grab the hash. I'm going to go to new tab, and I'm going to paste it in. And what you're going to notice is, pay attention to the loading bar on the video. You'll notice that it's playing back before it's fully downloaded the file. So it's streaming it in. And you'll notice that it's continuing to download data here. So that's pretty cool. So there's a little bit of extra code to do that that I didn't show you guys, but it's pretty straightforward. You just do when you do pipe, you just pipe to the video tag instead of piping to the concat module. OK, cool. So yeah, that's instant.io. One other thing you can do with WebTorrent that's pretty cool is, like I said, it works in Node. And in Node, there's a command line a program that you get when you install it. And it's called WebTorrent. So you just do npm install WebTorrent-g for global. And then you can actually use WebTorrent as a console program. And so what I'm going to show you guys here is one cool thing we can do. So I'm going to invoke WebTorrent. Where's my mouse? There we go. OK. So, all right. So I'm going to invoke. Ah, geez. 1 second. What happened? OK. All right. So I'm going to call WebTorrent, pass in a torrent file, and then I'm going to add --VLC, which means please stream this into VLC as you get the data. So when I run this, this is funny because I asked Fred to, who's the guy who is making the Wi-Fi work awesome, to give me privilege to use BitTorrent because it was blocked before. He also gave me 1/3 of the capacity of the whole Wi-Fi network for this. But it's still a bit slow for some reason on this network. I'm not sure why, but if we give it a moment, it will eventually find some peers, and then it will stream the video into VLC. I'm gonna leave that going for a sec. All right, if it hits 1 minute, then we'll move on. Oh, there we go. Found some peers. Awesome. Okay. Now, where's VLC? Here it is. So what this is doing is it's actually created an HTTP server, and then it told VLC to play video from that HTTP server. And as VLC makes range requests for video data, the BitTorrent client watches the HTTP server, and it sees, oh, they want this particular bit of the file, so we're going to go get it from the network. And anyway, so it's some encoding artifacts. Anyway, it's streaming it, and if I were to seek to, that would work as well. It would just suddenly realize I'm asking for a different part of the file, and it would go and get it. It's really cool. It also supports a -- like AirPlay flag and Chromecast if you want to stream to a Chromecast. There's lots of cool things like that. So last thing I want to tell you guys is a little bit about how we get the same code to work in Node in the browser. So this is kind of what the dependency tree of modules looks like for WebTorrent. And there's 3 modules in particular that we need to change to work in the browser because, like I said, WebRTC is a bit different than TCP and UDP. And the way we do this is we substitute these modules out using the browser field, which was actually mentioned in a talk yesterday about Browserify. And what we do here is we say, when this module is being bundled for the browser, please replace these modules with these alternatives. In the case of the DHT one, we put false because that's actually not been implemented yet for the browser. So we just say ignore that. Please don't even include that. But for Tracker and Swarm, we're actually going to talk to a different tracker, and we're going to handle the peers a bit differently. So remember, TCP and UDP is really simple, just an IP and a port. But WebRTC, I don't have time to go into this, but I just want to show you a little bit about what the flow looks like to do a WebRTC connection. It's insane. This is, I kid you not, you have to do all these API calls in the right order and listen to all these events to make a connection happen correctly. It's insane. So I encapsulated this into a really nice module called Simple Peer. And anyway, so this is what we do differently for the browser, and that's handled by that browser field. Okay, so anyway, I want you guys to go out there and build applications using WebTorrent, and find bugs in it because it's really new, but I think it's really exciting, and I think it points us to a future where all applications will be peer-to-peer, and where we can bring the internet back to this place where things are decentralized and there's not this kind of like corporate ownership over this infrastructure that's so essential to human freedom and to like good things in the world.
Yay.
So, thanks.
Thank you.
Thank you.
Please make sure you ask at least one DHT question to Feroz later on when you grab him. Thank you, Feroz. Thank you so much for really waking us up and showing us the wild, wild web and torrent.
Thank you.
Next up, we have...
Me.
Yes.
Hello. I'm here in the back.
Thanks.
So I have to shamelessly plug something after his talk about WebRTC. He has a really cool company in Singapore called Timasys. They're one of the sponsors as well, and they built the free Internet Explorer and Safari plugins for WebRTC so that these things actually work in the browser too. As you can see, I'm using Safari here. This is Safari, and it's working with WebRTC. And to show you, if you go to this address here, getaroom.io/devfest, and your Chrome browser or Firefox, or if you have the plugin installed even in Safari or Internet Explorer, the first 2 people that go on that will be able to show up on that screen there. So let's see. Oh, we have 1. Who is it? 2? There we go. You're the 2 lucky ones. Roman, hi. Good to see you. So that's working. This is like how WebRTC can work. This is the Skype as a feature part that Feroz talked about. And if you want to explore these kind of things and build something yourself with it embedded into your website or app or application, please go to this website, which is the open source website from Timasys here in Singapore. And the platform is called Skylink. It's all open source. You can embed it into the app. Even the source code of this Get a Room demo is built with React, and it's free. You just click here, fork me on GitHub, and you get the code. So play around with it. The two developers of Skylink.js are here as well, Let and Tan. You may stand up over there on the right side if you like. Like, you can ask questions. Don't be shy. There we go. So yeah, check it out, play around with it. It's pretty powerful. It does the data channel and everything as well.
About the location of the file. So in this case, the file lives at example.com. And it's our job to go and find that server and then to ask it for the file that we want. And so as more clients show up, they continue to go to the same location and ask the same server for the file that they want. Eventually, you get to a situation where the server needs to either upgrade to handle the number of requests that it's getting, or it's not going to be able to handle them all. Another issue that comes up with this model is if the server disappears, then we can no longer get the file because we're referring to it by its location. So if the location disappears, then the file is gone, and this is the jetted broken link that we all see on the web every day. Oftentimes, too, URLs will change. So the file is exactly the same, but somebody decided to name it something different or put it on a different server. And this is also undesirable. So in the BitTorrent model, we don't have a server at all. We just have clients. Everything is a client. So at some point, a file, somebody needs to decide, I want to bring a file into the network. So there's still an initial publisher, because there has to be. There has to be a person who says, hey, I want to share this file with people. But instead of putting it onto a server and then sharing a URL, what they do is they create a torrent file. And they become what's called the initial seeder. So a seeder is just somebody who is making a file available and sharing it. And they're the initial seeder because they're the first one doing that. So when clients come later on and want this file, they connect to the client and they make a request and get back a response. And this is very similar to HTTP, except it uses a different, different protocol. So we have a method, and then we have a piece index, a byte offset, and a length. And these are kind of similar to an HTTP range.
Say that you had inappropriate content. So I really like, like this kind of thing, and I'm also a big fan of Juice Rap Media.
And it's not even just torrents anymore; it's magnets that get you the torrent. Magnets. How the fuck do they work?
We've been publishing the magnets. In fact, isn't the next story about this lady that blew the whistle on the Fed, and I've now uploaded that to torrent, so it's now immortal.
Very cool. Exit question: yes or no? And this one's for the viewers at home too. Will you help me change the world with YouTube? Will Penguin?
Yes.
Christoph, Atlas.
I'm in.
All right, Blake Anderson.
What was the question again?
To say yes.
No.
No. Bryce Wiener.
Take your shirt off.
They're saying that now. Chris Ellis.
I think I'm going to quote Camus and say, you can't change the world, but you can change the way people think.
And I'll quote Groucho Marx. I wouldn't want to be a part of any club that would have someone like me as a member. Moving on. Issue 5, bonus issue. Federal Reserve leaks tapes. Federal employees were told not to ask questions, not to regulate banks. A culture of failure. New tapes
So I think that YouTube, if we can get a situation where people can talk back and forth and make shows and then come on each other's shows, and that we can have a decentralized system of communication and entertainment instead of all this unilateral programming that, you know, everybody's depressed and on antidepressants and gets all these messages about war and death and genocide and Ebola and all this shit. That's a nightmare. That's nightmare shit. We need to start to get away from that and realize that negative programming affects you negatively, and positive programming and working together in collaboration really makes people feel better, because you can feel the traction of shit actually getting better instead of just being entertained to death into your grave. So I mean, I think it's good. I think that everybody should join the World Crypto Network and donate and work together and become part of the shows, and that we should usher in a good version of the future.
Bryce Wiener.
I think there should be more boobs on YouTube. I think YouTube should allow porn, and I think that until they stop editing content, it's all just so much bullshit.
Chris Ellis.
Yeah, I'm actually really optimistic about BitTorrent. I'm looking forward to this becoming a little bit more mainstream. So I'm really into torrents again. I don't know why. I just suddenly got into it because I think somebody sort of said to me that, you know, they've got Merkle trees in there. I was like, oh, cool, really? And so I started looking into it. I started putting everything up there because I just like the fact that it's distributed. And so now this app, apparently this open source project on GitHub by Feroz, is claiming to stream video through a web browser with no plugin required, just straight up through the web browser. It will stream you a video torrent. And I want us to do this on the World Crypto Network as soon as it becomes feasible. I'd like us to really do this because I don't think we should be dependent on you know, YouTube's great as far as it goes, but it has been known to shut people down. People can troll you. They can also petition for you to be taken down, and YouTube just take you down automatically because they got like 10 different IP addresses to.
I turn my camera on, I cut my fingers on the way, and you wasn't polite.
So hey everyone, I'm Feroz, and I want to tell you today about WebTorrent, which is my open source project to build a BitTorrent client that works in the browser. And this is kind of madness because BitTorrent is not something that has ever worked in the browser, and so the project is definitely in the mad science realm, and it uses this awesome peer-to-peer protocol called WebRTC that has recently landed in the browser to enable this. But before we get too much more into WebTorrent, I wanted to talk a little bit about how BitTorrent itself works, because I think it's something that we all use every day. Well, a lot of us do, but it's you know, something that for a long time I didn't really understand on a very deep level. I kind of knew, you know, high level that, you know, you have these people out there that have the files that you want, and you somehow connect to them and they send you little bits of it, and then you kind of like put it all together on your machine, and then you have the file that you want. But it's actually kind of cool to kind of look into how the protocol works, and so I thought we would talk about that first. So traditionally, the way that most of the services that we use every day work is the client-server model. So you have like an HTTP server, and you have a client that connects to it. It sends it a request asking for a specific resource. So in this case, file.txt. And if the server has it, it'll send back a response containing the file. And the way that we refer to all these files is using something called the URL, or a uniform resource locator. And the URL tells you where to go to get the file. So it's all about
to transform the news. Is YouTube more than a collection of cat videos? Is it a force for social change? Do channels like Juice Rap News, The Fucking News, Mad Bitcoins, and the World Crypto Network provide more than just entertainment? Can they actually provide the truth? If the medium is the message, and it always has been, is it capable of being truthful? And can we use this truth to bring about social change? I'm laying it all out on the line here with this question. Can YouTube change the world? Will Pangman.
I think if they change the way incentives work for advertisements, for revenue, for the content producers, and do something, maybe integrating Bitcoin to perhaps upvote good quality comments and get rid of trolling, then yeah.
Christoph, Atlas.
Yeah, it already has. YouTube is just a way of connecting people in a more peer-to-peer fashion, exchanging ideas, information, and all that stuff. It's the natural progression from the printing press to all the things in between. And of course, there are things that we can do to improve YouTube around including Bitcoin and change tip and all that other kind of good stuff. But yeah, it's been doing that for a long time. I've been getting the majority of my information through mediums like YouTube for years at this point.
Blake Anderson.
Well, yeah, I've been railing against unilateral communication for a long time. I think it's important that people can comment and respond to articles. Every time I see a modern digital publication that has an article with no area for comments at the bottom, I was like, who is running this disaster? There's no place for comments.